Yeah, Coffee Compiler Club. It's a small morning here. Cameron's coming back and forth. He's getting internet connection things. I claim, sir, it's your cloud connection. Um, there you go. You're back. It's
Yeah,
the whole cloud
press
connection.
the wrong button.
Uh, so I declared chapter 19 sort of done. There are a bunch of holes left in it for future extensions that are pretty easy to go fill. Like the x86 memory operands, I did them for add and loads and stores and a few other things, but like and or mask XOR shift left right all do memory operands. It's just like they all be like another line of cut and paste. Um, but it looks like it's producing reasonable instructions out of the x86 side. Tommy's not here. I wish he was. He's busy trying to do a RISC-V port, which I will probably add on to chapter 19 technically when it gets there. And I closed 19 and declared time for register allocation. So I was going to throw out a demo of x86 instruction selection on a few pieces of code, and then that was all I had for a starter, and then people can ask questions or not. Like, where's Matt when you need him to come pester you about why you're not doing SIMD? Um, ease. Okay, let me figure out how to and then if anyone wants to say anything while I'm setting up here, I'm just going to figure out how to get the damn IntelliJ to do a presentation that's reasonable. That might be reasonable. And then it went away immediately. Why? Try again. That was weird. Yes. Okay. And then 19. Right. Okay. Let me find the share button. Where are you? Zoom. Share. Maybe. Yeah, right. Um, so like one of the major flaws I don't have figured out here is how to write decent test cases for this stuff. So I am hand reviewing things. So let's go stare at this for a second. So here's some piece of code. It says arg plus one times, arg, and and out of this, I've decided that there is a plus one as an increment and a multiply. And then these are all virtual registers. And they're exactly node numbers out of the x86, out of the simple nodes. But you might as well think of them as virtual registers. So arg comes in virtual register in 9, and the increment will force our same register in and out because it's an x86, but in the virtual register number field, that doesn't show. So that's a job of register allocator, take care of that one. And then there's a multiply and a return. So it's pretty obvious. So let's grab something that's a little more uglier.
So the next step would be mapping the virtual register to actual register by
Yeah,
the
uh,
register locator.
right. That's register allocation. Uh, so what did you not do here? Why? Again. How about now? Oh, there it goes. So here's some code. It says something stupid. A equals arg one, arg plus one, B is arg plus two. If arg is one, do something else, something something, something, and add. Like, okay, it's a bunch of junky adds and stuff. But here is a compare of node 10, that's arg, and that'll be flags in 8 here. That'll just be flags. That's a register in the register encodings. And so then there'll be a jump equals on flags. And you're going to load up a 5 or you're going to shift by one, because if you look at the math, you're adding arg and arg and arg. You get two args or three args according. And then there's a 4 for the other guy. Here's some phi functions. They don't have any encodings. And then some adds to fold it all together. And in
So what
this,
what we will do with the phi functions?
they don't print as anything. So on the left, I have an address of where the instruction starts and the encoding. Well, I don't have any encodings yet because I don't have any registers.
Mm.
So all the encodings are pretending that they're 1 byte of question mark, which is of course baloney. So an encoding will come after register allocation, but the encoding is sort of it's nitpicky and careful, but it's all stupid as well, if that makes sense.
Mhm.
So you have to do something for it. And on an x86, you have all these mod RM flags and bits and bobs you can put SIB bits. But they're not very hard. So what you'll get is at some future date when I do encodings after allocation, you'll get a few hundred lines, maybe not even 1,000 lines of how to do encodings on an x86. Hey, Matt. And so, this will become real numbers, and this format will say, whatever your address is, plus bunch of bits for your encoding, and then this will be the right-hand side will probably be the same. The jumps are all bogus in that there's no real control flow graph yet. There is, and I just throw a jump in between every possible basic block. But after the allocation's done, I'll know that some blocks are empty and some are not. And then I'll arrange fall throughs. So part of the encodings will come through with a block layout to arrange for good fall through cases. And then all the extra jumps will just go away. So they're listed as all capped because they're sort of virtually jumps at the moment. Um, there's nothing actually going on with them. And then later, when the layout happens, you won't need a jump to a jump to a jump kind of things. This guy jumps to 3 down here, which is fine, but this jump to 3 goes to the very next block, 3, and he'll just not have a jump there, just be a fall through. So looking at this kind of a thing here, the kind of odd things are that flags are actually just another register at the moment, and then the jumps are weird. So let me go do a couple more things that look a little nicer or do a little more fun stuff. We're going to get to array. Let's see if this guy will do it here. Get to arrays in a second here. That's the other guy because I have to redo this. Yeah, right. So here is sum is in a loop. So args in N14 and you zor out I to get a 0 for I, and there's an I for a phi and a sum for a phi, and a compare if you're not done, and an increment of I, and an add of, the sum and the prior version uh, in the loop. So it's pretty straightforward here. So let's go grab something that does, so here's Leah's and shit. We could do that. Let's do this one instead. Ink a little bit nicer here. And then I'll talk about the registers, how they're defined. So this guy says, load up the length. So alloc here, what is alloc? Alloc is basically a call to malloc or to new allocation if you're a GC. And I'm stalling the allocation decision because I can't. And I can stall it all the way out to the bitter end. Um, it's expecting you to pre-zero, and that's about it. So I want 32 bytes. And then I'm taking arg and I'm anding 1. And if you look at the code out here that I'm busy doing things with, there is arg and 1 as a load, as an array load. So after the and, here's a store 3, that's the length, and the first 4 bytes of my array. So I have length checked arrays, and the first 4 bytes hold the length, and that can be changed to be 8-byte indexed arrays if you like. And I don't have range checking put in. Um, so at some future date, you can get proper range checks. And then I store a one into the argth location. And that's the full x86 fun addressing mode. And then I'm loading from my ANDed, here's the index, which is the ANDed value up here, and returning. So I can do things with full on x86 addressing modes. So let's go see a little bit more of that kind of thing. Um, do not here. Where did it just go? This is because this guy's crazy. No. Yes. How about now? Okay. Give me a little thing here. So the loop says fill everything with array sub I, and then rolling sum, grab from the prior and add one more to the next guy. And so somewhere up here, I'm like, how big do I want it? Well, I want it as big as arg with 8 bytes for my 8 byte integers plus some length padded out. So you get +8. And then here's a mask that should be just a ZX. It's just a zero extend. And that just says whatever arg is, I'm treating it as an unsigned integer for purposes of the array length. And that's how the definition for arrays go, is there it's an unsigned integer, 32-bit integer. Um, so the actual array length is considered the unsigned version of arg. And then there's a first loop. Here's jump to 8 to 8 here, right? Here's the first loop. And the first loop says, whatever you expect, compare to, my 0 to arg and store I in and increment I and loop. Pretty straightforward. And then there's a little hand wavy work to set up for the next loop. And then he says, go load from one, go add from the other, and store it back down. And I could probably work to get these two to fold together. And they're not right now. And I actually kind of thought they would. But, it's loading from one and writing to the other. It's pretty straightforward here. You'll notice that there's an offset. Oh, these two aren't folding up. Oh, I know what happened, why this didn't fold up. Here's the +16 and here's the +8. That's the address math being folded up. Anyhow, when that loop's done, he's just down here where he says, grab from one element and grab from another element and do a little shift scale math so I can read out the answers as a reasonable answer in the simulator. And oh, look, right down here at the bottom, the store of the array length happened. It's not necessarily array length has been hoisted out and everyone knows the array length is actually arg. So even though the code says go array length, it's actually known to be arg. And so the actual, oops, come back here. The actual generated code just takes it as arg directly. Although when I finally come out to returning the answer in the end, I go ahead and finish out the array definition by putting the length in it. That store is just free floating. It could happen early, it could happen late. So that's sort of the obvious things. I can totally do uh, brain fuck and merge sort with this thing, and he allocates reasonably. Like here's sieve. I'll do sieve here for the last example, and then I'll talk about what you get out of register choices here. Okay, so here's C. There's a couple arrays up front, including an array of bools. There's, suggestively named fees for things. And here's the squaring that for the first loop that says p squared less than arg. And go test some bit. And you'll see that there's no scaling since it's all byte arrays. And increment and run in a loop until you find your primes. And then there's where's my shift +1 here? In primes gets added. One of these is going to be set the prime in a hot loop. Where's 16? Oh, it's right there. Yeah, that's it. That's that 4p squared. I listen there. Plus equals p. Erase by is true. Here you are storing primes into it. And then there's some collection down here where there's going to be another loop. Where's my second loop, third loop here? Testing a prime. That's going to be testing a prime. Oops. And store things into where you collect your primes. And then there's an array copy way at the end down here where I allocate. Where's my new alloc? Here's the new alloc for the array copy. Here's the array copy where you collect the primes into a dense array and return it. Anyhow, it's you can pick things out pretty directly there. It's pretty straightforward instruction selection.
Cool.
So
One question.
yeah,
Yeah. Somebody, somebody did something. Oh. So right now we do not optimize tail calls a function with
I'm
into a
sorry.
loop.
I don't optimize what?
Tail call elimination, a function that calls
Yeah.
itself
Oh
into a
yeah,
loop.
right. I mean I could, but no, I don't. So, but it's
Okay.
not hard. This is the deal. This is the thing that frustrates me about hotspots. That 25 years ago it was 2 weeks away, and then that never happened. Fine. Um, the actual calls track the necessary information directly in the IR. So
Mm-hmm.
I do have the return PC as a explicit value in the IR, and that is directly what you need to use to feed forward into the tail call elimination kind of thing. So
Mm-hmm.
yes, the IR supports tail call elimination. It doesn't have it implemented right now. If you felt the urge to add it, you can feel free, and I'll take a PR. There's
Mm-hmm.
a bunch of optimizations not done because this is just how far it's gotten.
Yes. Yes. Okay.
So there is a portability thing. Um, so I need a couple of things to be portable, and this list may change, but I don't think it'll change very much. So there's, hey, this is x86-64, and then this is how you'd call your registers. And if you're a register allocator, you need to be able to make a split instruction and a jump instruction and something special to break infinite loops, which is a version of a jump. And then the instruction selection guy. And that's, what I need to have ported. There's a second piece of porting, um, which is a machine node, which is do things with individual idealized nodes that become, fancy. That the main ones will be given a node and an input number, tell me the register mask, the allowed set of registers on that input and on that output. And if you're a multi-defining op that you produce multiple values like a div rem, or your subtract that produces flags as well as a subtract, I need multiple outputs. So I have to tell me which output gets to which registers. And if you're an x86, you frequently have two addressing mode, and that means one of your inputs becomes your output, and which one it is, and the register allocator cares about this. He will force those to be the same. And then there's a hint that says this instruction is cheaper to clone than to spill. True for like all kind of small constants. And then I'm going to want an encoding out of you. And then this is a pretty print visual version. It's not an encoding. It's a assembly readable. That's what you've been looking at is the ASM outputs. And then a short opcode name, which, call or load for or whatever. So those are the kinds of things I need. The the machine for an x86 has a name. Version 2 has a bunch of registers. And has a bunch of XMM registers. And all the register numbers don't overlap, so flags at 32. And there's bit masks for obvious sets. So I can read from any of the GPRs, that's an R mask. A W mask won't let you write to the stack pointer, but it lets you write to any other register. And then there's X masks, and there's something for flags, and then there's a bunch of calling convention things. So these are all fixed because they're going to show up in the calling convention somewhere. Here's your pretty printing string names for the same. Here's calling conventions according to sys5 or Win64, and then you get this, which is given a register number, here it is as to where you land, and then it varies according to Win64. And this is, yeah, that's correct. Um, and then there's some call or save things that I probably need to put into the machine as I need the call or save list for the register allocator directly. And he'll ask for that and get the kind of things that are call or callee saved. He'll turn that into the correct set of live ranges so that when he spills, your call or saves are preserved or not. So you get all your different calling conventions here. Um, these are all kind of short in the sense that I just stopped after 6 or 8 arguments, and they'll just crash if you try to pass more than 6 arguments. And the extension for them is typically they go to the stack, and there's a way to specify how to put things on the stack. And I was going to wait until I had a register allocator. It was going to do that, so I don't have that stuff there. Same for the other things the machine guy needs. I don't have them because I don't have a register allocator in place yet, but they'll just be make an instruction that looks like a jump or whatever it's going to be. Then the actual instruction selection has this big ass switch, which says, give an ideal node on the left, go produce something on the right. And about half of them are just like, you get one choice. It's very obvious what that choice is. Some of the choices are nothing to do with x86. They're just a copy of the, supporting node. And one of the things going on here is that I am copying everything from the old space to new space. Uh, registers are, or not registers, nodes in the ideal space get remapped to new numbers, new nodes, new address, new space for the machine ops. And then the little functions here do something clever if there's something more fancy to do than just a straight up pick another node. So things like add have all kinds of fanciness to them. I'm gonna go pick something simpler than add for the moment here.
But
Uh,
the return type is node, so all the remapped operations are also nodes
yeah, it's
on the
just
right
nodes
hand
to
side.
nodes,
Okay.
except that the remapped guys will be about half or two-thirds will be some flavor of an x86.
So that's maybe that is the lowering step, mapping to the IR to the specific machine instructions of x86, for example. Yes.
Say that again, got it, but I think you got it right. Yeah.
Yeah. So yeah, it is the case for mapping from the IR nodes to a machines to x86 equivalent
Yeah.
nodes.
Yes.
Okay.
Yes. So it's just nodes on nodes, but the x86 ones will be generally implement lock node. They'll support an encoding. They'll support register masks and the like.
I know it's generally not meant to be mixed up, but at this point, the graph can be mixed with all kinds of nodes. Some of them can
Yeah.
be x86, some of them can be IRs, and it's all a mush together.
It's a little more clean than a mush. So this is the head of the function call, and here's the call that does an obvious mapping. Everything to the prior to here is only ideal nodes. And like Cameron lost out again. It's only ideal nodes. And
Okay.
everything after this call is a blend of some ideal nodes for things that make no sense as an x86, like phi functions are generic for everybody. It has nothing to do with x86.
So we don't do anything with them. We don't emit code for them. We just remap them. Why?
Yeah,
Why
yeah.
why why not just delete them? So why
Because
do
they can't, this keeps the graph in a pure SSA format.
okay.
So every input is, and the register allocator cares a lot. So the register allocator knows that things that are joined by phi functions have to have the same register.
Okay. But
And so if I have an input that takes something from a fee, I still have to have a register for it. If I delete the node, then the guy who would consume from a fee doesn't know what he's consuming from. Like he
hmm.
has to know where it came from.
So
So
this is the requirement to keep the graph in the SSA form, or there
it's
is another.
the reason for being in SSA form is that you need to have the full complete graph to do register allocation with.
Okay. Hmm.
That fee function shows up in the register allocator in a big way. It's all about how do I, how do I pick registers or who says what? So we can go run the look at like sieve of Arathesses again here. Um, so here's a view without the encode with the ideal with x86 encoding guys, but not done in an assembly language format. So here I have some sort of a loop. Here I have a bunch of fees in the loop. Here I have this multiply, which comes from a fee. This is the squaring operation where he says p squared less than arg. Okay, if I delete the fee, what does 41 point to? Well, it's pointing to the fee right now, but what if I delete the fee? What does it point to? Where does
Hmm.
Mold know that his two inputs get some kind of register? And it turns out it's related to P, and P gets modified throughout the loop because there's a P plus plus, in the body of the loop here.
Oh, yeah, I get it. I
Okay.
kind of get it. Okay.
So, so the,
The semantics are still in the graph, but are there to support figuring out what are the what is needed.
yeah, the instruction selection does a tiling over the ideal graph, replacing some tiles or groups of ideal nodes with machine-specific versions.
Hmm.
But every node in the original graph is either tiled over and replaced or copied directly into the new version, the post-allocation version, the post-selection version. So no node gets dropped. Everybody gets carried over either as a fee directly, same as a loop header, same as a function header, or return op, and or they've been hit with an idealized tiling mapping so that you
So
get.
at this point, the graph is still amendable optimizations, but does it make sense to, or all optimizations are done at this point?
Well, the pretty much your register allocation is an optimization if you like, but pretty much it's considered done at this point. If you had things that you coulda, woulda, shoulda do, usually I do them either in the ideal graph before or occasionally in instruction selection. So the instructional selection has a lot of choices about how it picks things. And
Mhm.
he will make choices like, I'm going to use an increment instead of an add one because it's a faster, shorter, tinier op. But he makes these kind of decisions.
In
Or he
the
says,
instruction selection.
yeah,
So what is how it's based its decision what is faster
yeah. So
instruction than
it's
others?
purely a greedy thing. That I
Okay.
did a Burj allocator. You can go look up what Burj means, bottom
Hmm.
up rewriting system, but it was a pain in the butt, and I'll never do a Burj style thing again. Just greedy and be done. So instruction selection says I have a hash map and I'm mapping node to node, and I'm going to take things from the old world and look them up with a map. And if I found that I've did it already, then I've been there, done that, I get out. I've already remapped this guy. Otherwise, I'm going to ignore this for just a second. I'm going to call instruction selection on the old guy in the ideal world, and he's going to hand me back an X, which is a machine specific version generally. It may be just a straight copy for a fee, but if you're an add, it became an add x86. And I'll put that in my mapping, and then I'll recursively walk your inputs doing the same thing. And then, there's a little post cleanup for things.
When it made sense to remap, just point to the node because we saw the you are remapping the fees by constructing a new fee with the same content. What is there a benefit with remapping that fee to a new fee?
I want to cleanly separate the old space from new space.
Uh,
So
hmm.
it is not
Uh-huh.
there. There's no other reason in C2, there's arenas here, and after the remapping, you throw the old arena away. You reset the old arena and use it for the next round of whatever you
Mhm.
need a big old arena for. In Java, of course, it's all garbage collected and you don't technically need it, except that the cleanliness of everything in the old space is gone and everything points to the new space prevents you from accidentally finding bugs
Yeah.
where you
Yeah.
cross-link the wrong versions.
So it's guarding because the new nodes will have a different numbers and
Yeah, yeah,
yeah. Okay. Cool.
yeah. There's no pointers left over from the old space when I'm done.
Oh, okay.
Um, and then this little clause happens because some of my expansions produce the tiling is M to N. You'd like to think it's one to one, but it's commonly the case that it's several ideals become one x86 because you have these fancy addressing modes and you do a shift scale add all baked in. So you get this mini ideal to one, but you get the reverse where in the case of flags, I'll have multiple x86 ops. And then in more recursive walk, I will discover that I'm walking an x86 op, in which case I need to say, oh, this new node is actually, I mean, this I what could have should have been a old space ideal node is instead a new space because I have a multi-part expansion, so I just need to walk the edges without actually doing a mapping.
Mhm.
And so these come into these different things here. Let's go find my simple one. So here's a guy that I don't even have the other version of because no one wrote the code that hit it. But he just says, I'm given an and node. If my right-hand side is a constant node, it better be an integer. I should just assert on that one because it's an and. Then I'm making an and I. So an and immediate. It's a mask. And he just produces a mask out of that. So that's the common kind of remapping rule. Let's look at an and here. Uh, these are generically, many of these guys look all like this guy here. They say, I'm an and I'm some sort of extension of a mock concrete, which is a very common base class. It just gives me some cheap, easy things. Uh, wow, that spacing is terrible here. What happened there? And then you go ahead and clone yourself from the prior, that's your constructor. Because you have baked in the immediate, I don't need the constant input. So I throw away the constant input and the and has the immediate already baked in. Register mask, he's only got one. I assert you're only going to call me with register number one, and it's a right mask. Oops, right mask. The output's a right mask. The input and output's two addresses true. They have to be the same register. There's a pretty print right here, and done. And, very, very simple, straight up dude.
The addressing modes are going to be interesting, especially if you are doing more than just x86, but for example AR64. Because a common mistake is to assume that you are going to have effective address, which you have on x86, but it's totally different on how you use memory addressing in AR64. You have this modes of addressing offset, pre-indexing, post-indexing, and then you can shift some of the selected registers, and then you can also add offsets, but it's very different than the you actually have these addressing modes which are pretty complicated right inside the ARM instructions for load and store. So to make effective use of that, it's actually very useful not to have an effective address node, which is x86ism.
All right. So the x86 port has support for x86 addressing mode. Um, but that's not ARM, and ARM would do something different then. So the common behavior here is I'm going to have a memop x86, and the memop x86, which people are extending, if they have one of these, has offset and scale and immediate, declares something about whether it's 1, 2, 4, 8 bytes in size, and does a bunch of things to do with cloning or picking up all the body parts to make up an addressing mode. Um, Store ops or other whatever opt memory pickup of value edge as well. And then there's some register mask games to go with your different inputs. and here's your generic pretty print for the address,
So
right?
adding and shifting that I expect may be still similar. You may have memory ops in AR64 that could kind of sort of map to this, except that in addition you also have side effects, like you are allowed to do pre-increment,
Yeah,
increment, pre-decrement, and post-decrement on ARM.
yeah. That's
For
not
loops, that's very useful. For example,
right,
you can
right,
advance while you are indexing in one instruction.
right. That's not allowed or disallowed, but either way, like this totally is doable. Um, in the instruction selection job here. Let me see. Zoom
Okay,
in.
so if you had like a generic memory op, machine independent without it, then you could still, I suppose, fuse it into machine dependent memory
The
op and side effect on
yeah,
AR64 side.
the instruction selection guy's job is to pick up those fuse pieces and do something with them.
So you
So
basically would be doing some simple form of peep holing, almost kind
yeah,
of.
this is
Uh,
right. Greedy people things here. Let me find a better case here. This guy, where's my, I had one that was doing with the store. Yeah, here you go. So store of an ad of a load will do a side effect to memory. And that's the same as a standard x86 guy, except they're reversed. It's mem add instead of add mem. But it's the same kind of game going on here where you'd say, and also I see that the value field has a increment with it, and then I can you could do this on an ARM. Um, and in fact, certainly C2 does that directly in x80 hotspot. So the actual encoding game here has no requirement to say you can or can't do an addressing mode with a post increment or not. It's sort of unrelated. You have to sort it out yourself. But there is some straightforward way to say, hey, go make me a thing that does something with a store and an ad and a load. And that's what's going on here. And the actual encodings are all very straightforward here. You know, base plus offset, and you get the ASM print. So it adds like prints like that. And then this printing for increment or decrement or add is all about sometime later, the encoding guy will choose whether you're doing the increment or decrement version. What else was I doing here? So, basically that's sort of what happens here. He just looks at patterns and says, "Oh, I have a x86 version of this, and here's how you go." And you get fancy for things like load op store. Like this is here, I only have the add in, but you could put multiply or sub or XOR or whatever there, and it would all be the same kind of thing. Add has one other weird mode for Leah. Where's add? So add from a load gets me an add from memory. And I didn't do the reverse side, but that's just like a cut and pasty. And then there's an add that says, oh, I have a offset. And then as in the other side is another add of whatever. Okay, you go to Leah. And then there's a shift. Oh, go to Leah. Otherwise, you get to add immediate. Otherwise, you go to Leah. What the hell's Leah do? Leah says, well, I'm looking for a shift. And if I find it, I'll do shift scale add things. And otherwise, you end up with an add or a Leah. And the add is, super straightforward. Uh, two inputs, read masks, one write. First input has to be the same. Here's the pretty print. Done. Where's the Leah? Come back here. I'll go to Leah. Leah is the non-mem opt version of the same thing, which just does all the math. He grabs all the things. He's swallowing in all of the parts, so he resets his inputs because he's going to have them baked in. And then he just has a pretty print version of the same thing. So nothing, it's kind of like bit fiddly, but it's not really rocket science.
So what's up with MOV node? I saw
But
some
small node,
discussion.
sure.
MOV. I saw some discussion
Oh,
about
I'm sorry. Mul or
move, the move
move?
instruction. Oh,
Oh, there is no move because I don't like it. Oh,
why?
there you go. So no, so the problem with move as an acronym is that there are two common x86 encodings and they flip which direction move means. And I just was like, I didn't want to have this conflict with people like looking at the output and saying, "Oh, I come from an Intel ASM or an AT&T ASM background, therefore this move means this." And no, instead, I don't use the word move. So at every time they have to stop and look and say, "Wait, there's no move." Oh, but this says load 4. This says store. So that, it's telling me what goes on already. So I don't have any move ops. Um, and that's
So
just a naming.
move, load and stored obsolete the move.
Load and store replace most of the moves. So there is the spilling code will end up with a reg move. And I'll have to put something in that technically looks like a reg move.
Mhm.
And that one probably will say move, and I'll have to try very hard that the pretty printing of it is not encouraging you to read it the wrong way because you come from the other background.
Maybe you
But
can call it transfer. You remember 6502 had transfer index register to accumulator TXA.
maybe. Yeah. But right, but there's a point there that you're just trying to like not confuse people. That's it. And another funny thing is that uh, until you get to the register allocator doing splitting code, you don't need a move because it's SSAs. You've already folded all moves up completely away, so there's no moves. Um, let me pull up one other funny thing. Let's see here. Parm parameter. Parameter calls call mask based on his index number, and that's where he basically says register parameters get fixed a known fixed address based on calling convention, and the calling convention here inside of hotspot there's a calling convention for Java to Java. There's a calling convention for Java to C. There's a calling convention for Java to the interpreter. And so basically, C2 supports three different calling conventions, and given a signature, he produces a calling convention that does the mapping layout, and he has another version which just produces little stubs to map between one layout to another based on a signature, so that if any point he needs to call from an X flavored to a Y flavored thing, he just dumps through one of these little stubs. He makes them and caches them and holds them off to the side as a little piece of
So,
assembly to just do register
so
shuffles. Yeah. So it's basically
interoperability
trampolines for
happens.
any flavor to any flavor internally.
Okay.
Um, and that lets him not care per se. So in the land of Java with x86s, the original C convention says like floats had to go on x86 int regs because whatever history, and but you had SSE regs, and so Java would just say, well, floats get in SSE regs, and but I can't call into C code that way, so if I have to make a call to C code or native or whatever, I need this trampoline game. Um,
So param x86 was the function parameters, or did I get that right?
Say that again. Yeah, parm is a parameter node.
Uh,
It's
for,
like
for,
it's like arg when I call from main,
okay.
it's
So
arg
the
comes.
theoretical maximum is the number of general purpose registers, and if you go beyond that, you have to spill them on the stack.
Yeah, right. So the register mask is currently not very well spec'd because we're just not that far along. Register allocation is coming up, but it will support a notion of a stack slot, which is just a numbered slot on the stack. And for calling conventions, it's common that you'll have, when you get too many registers, too many arguments,
Mhm.
the caller will put them on the stack. And the calling convention will say, oh, they came at register number stack minus 15 or whatever it's going to be. And that'll
Mhm.
be a valid register number, and he'll happily
So,
read it from the
so
stack.
technically, if you have a large functions, they will get more penalty because they do not they can't fit their arguments in all the registers.
This is always true for every calling convention everywhere. If you have
Okay.
more arguments than you have registers,
Hmm.
you run out. Yeah. But if you look
Okay.
at the Windows one, he only takes like four arguments and registers, which honestly covers like the 90% case fine. On the other hand, there's no reason that I couldn't have a simple calling simple. So simple calling C is a different story, but simple calling simple could throw every possible thing in a register.
What do you mean by simple calling simple?
When I emit code for a compiled simple method, if
Okay.
it, I know it's only going to call another compiled simple method,
Oh.
I get to choose what I want for the calling convention. And that
Okay.
calling convention could be all possible registers are available for all arguments. Okay. The calling convention could vary by call site.
Hmm. Hmm.
I
Hmm.
could first say, the first time I compile somebody, I'm going to pick the calling convention of most convenience for the guy I'm compiling. And then the next guy I compile who calls the first guy has to honor that convention. But it could vary from call to call to call as to what registers go to
But
where.
if you emit code with a certain calling convention, how would you how generally recognize what's the calling convention of
But
ready emitted simple?
yeah, so, some amount of the bookkeeping work comes out and will tell you what it
Okay.
is. Right? So somewhere in the world, there's going to be like, for instance, a mapping from register number to, I mean, argument number to register number. And that's a well understood layout according to, whatever your instruction encoding games are going to be. And as a table of pile of bits sitting next to the generated code, that's just part of the metadata to go with the code, including in that metadata shit like relocation information and linking information. When I'm calling C code, I have a call to malloc. I have some place in the code where there's a call to malloc, and register convention being all correct. Still, when you go patch yourself in, and you'll have to have somebody has to go find that and says, okay, here's the actual libso call to malloc, and here's the bits you call. Fine. So there's some metadata to be thrown in the encoding. You can throw in garbage collection bits, you can throw in stack trace layouts and frame sizes and all kinds of other stuff there.
Okay. Cool.
Yeah. Well, that was my chapter 19. Chapter 19. Here is instruction encodings. And I hope to see a RISC-V coming out after a while.
Hmm.
At some point, I talked to Ben Titzer, and he was like, "Ooh, you could do a WASM thing." And I'm like, yeah, I could do a WASM thing. All very
You could do
straightforward.
you could do LLVM IR.
There you go. I am not going to do an LLVM IR output. That is somebody else's grief.
Well, to give you
Do
WASM for free.
GCC. Do GCC. Exactly. Gimple.
There you go.
Gimple. Gimple.
I look forward to your PR, Matt.
Leaving this for you.
No,
Yeah.
no, Matt doesn't do PRs. Matt just provides you with whatever links you need to various papers.
Yes. Well, I'm all happy to let somebody else provide me a PR for that one too. I'm going to go find a way to make code and see if I can get it to actually execute it. There's a funny thing that says I could get it to execute inside of a JVM so that I could take simple from the Java command line as a program and arguments and just have it like evaluate it, generate code for it and evaluate it um, in the JVM as a native code. It'd be a humorous thing to do. All right, what else? Or I'll declare it done and claim we had all kinds of wild and crazy storms last night. I still have to go run around and do my house cleanup things. Lisa went to work this morning at the wee hours for Starbucks and had to stop and pull a log out of the road. It was the usual interesting mountain living experience. All
Hmm.
right.
Any more questions?
Oh, I've
No.
got
Fine.
I've got lots of questions actually, but I think they'll all be answered just by working through some of the examples.
Feel free to ask.
Yeah.
No, it's one of those you got to explore it firsthand to really get it.
I know, I
Yeah.
know. You
Yeah.
gotta screw around. Say, wait a second. And then
So I
otherwise
have
you
one crazy
ask.
question maybe. So if you somehow serialize the graph before its instructions selected, would it be able to have the instruction selection as a library to be able to instruction select for different architectures on the fly?
Well,
What do
I
you
mean,
think?
I currently have it set up as a let me where's the share here? Zoom share. I mean, I just grab it from a disk file dynamically here. Um, right here. You give me a string, CPU string, I go class for name you. That's
Mhm.
the encoding. So you could certainly throw down another port of a thing with a different name than x86 v2 and just go ask for it based on a string and you get that one. So that was my effort to say, hey, you can have as many CPU ports as you want. As long as they match the spec for a capital M machine, I'll just go run that code.
Mhm.
Is that answering your question?
Yeah. Yeah.
There's another version of that which says, uh, I want to produce a disk file that has ideal graph and then come emit for it later.
That was my question actually.
Yeah.
So
Okay.
serialize the graph until the point is to right before instruction selected,
Yeah. Right.
and then instruction select for a different for x86 for ARM for RISC-V.
Or change your calling convention from System 5 to Win64 to
Oh
whatever
yeah, yeah.
BSD. I don't know.
So would it work? Would it be able to Windows to be able to call something that can on the fly change the current convention?
Uh, yeah, this is like I pretty print the graph all the time as a serialized version. There's a denser serialized version that I don't pretty print, but I could, and then a reverse on it, which is make a bijection out of a pretty print.
Mm-hmm.
And then once you come up, you've skipped the parse step and the optimize step. If you look at my pipelines in the graph, it's all says parse, opto, type check. Then these now it says instruction selection, but you could stop after type check, spit the graph to disk, later load the graph up, run through instruction selection with a different choice. And then, following that is code motion, and then, register allocation comes after that. So there's a straight up set of things to do there. Um, I've long thought about, because stupid long history of how to go write dense versions of exe files. Basically, it's the portable compiler, portable assembly language formats, portable ANDF, whatever people had for ever and a day. Yeah, there's a
So
version out there.
yeah, maybe serialize the graph until that form, and the interpreter first instruction select and interpret the graph directly.
Right. Right now, if you don't do instruction selection, the evaluator is an
Can do
interpreter.
just that.
Yeah, exactly.
Mm.
He interprets directly. Now I
Yeah.
could go through and have those x86 ops all have an evaluation step in them as well, and then I could run the x86 instructions through basically an x86 fake evaluator.
Yeah. Yeah. Why not? Okay. Cool.
Right. But I think at this point I'd rather spit out code.
Could you do dynamic binary translation this way? Say you wanted to execute AH64 instructions translating live from x86, or would that be too difficult to do?
No, I mean we're all looking at an IR, and this is true for everybody's IR. It has, nothing to do with simple versus not. I think I have a fairly tight, expressive, simple version of things, but anyone's IR is basically able to do this kind of thing. Um, yeah, you want to play dynamic translation games, you can. Certainly in the C2, he takes it from, Java bytecodes, but he goes out to 5 different versions of x86 where he picks different instructions according to, what flavor he's running on. Or of course, if he's going to be an ARM or he's going to be a RISC-V or a Spark or a Tanium or God only knows how many. I did MIPS, I did a bunch of them.
So this layout seems much more lightweight than LLVM. Why LLVM is such a heavy machinery for optimizations?
Well, it's because LLVM doesn't have a champion and hasn't had one for 20 years. This is one of these things where the compiler keeps getting grosser because there's no one come along and say, wait, we don't need this yet again, or that another one, or something, just add another thing. Instead, every grad student wants to get a PhD piled on another thing.
So
And
what in our lingo, in the CF nodes lingo, what would be the equivalent for a bitcode emission?
when I'm coming to do encodings out, I'm going to call it encodings.
Oh,
I
okay.
mean, we're close, right? So
I think
I have register
bitcode,
allocation.
if you an LLVM bitcode, then that's a serializable format. You can save from the compilation and then you can load from the compilation, including saving and loading between compilation passes. That's useful for debugging the compiler, for example.
Yeah, I I could do that as well. It's not far off. This
So
is exactly what
I
Theodore did
think
a
the
second ago.
one thing that you would take some time in the simple as it is the use of globals, because you just have to take care to serialize those globals properly. And I'm not sure if you use something like indirections, but in C and C++, globals would be a disaster because a global could be a pointer, and then you would have to make sure to adjust the memory address when you are loading.
Um,
Something like relative offsets is usually much easier.
if you look at my use of globals, there's only a handful that have some sort of interesting state that, and the rest would not really be a pointer things. Like I have a bunch of temporaries, like bit vectors and shit. They get used for passes just so I don't have to keep allocating another and another and another. It's just the same guy resets. So he has zero state when he comes back in from a serialized version. The node counter is a number. And so that one has to be saved and restored. I did a bunch of global cleanup in the last 2 chapters. There's very fewer of them, and they're gathered together. There is the cogen as a global state, so I don't have to pass cogen to a billion places. But cogen himself internally has like, hey, this is the name of the x86 that I was compiling or the machine code I'm compiling, and here's the node number. Not very many other things. Let's go take a look. Like I said, I cleaned a lot of this stuff up. And I hear you, but this was all like known going in that, make life easier. So you use some globals, but then they're easy enough to track and gather. So here is the current compilation that would have to be saved out. It contains the last phase you did. Here is your source code string. Here is a known initial argument that would actually, once we get to the point where we have like a real main that has strings, you wouldn't have this anyhow. Here's your calling convention. That's the system 5 or not. Here's your node ID.
You know
There's
what?
a
That could be actually interesting, offering deserialization opportunity. Because thinking about now, you probably see a lot of those hobby compiler projects
Yeah.
also on like programming languages subreddit when people struggle which backend to use and they kind of cannot pick up LLVM because they come often from a completely different programming language than C++. And if they could use the simple backend as a backend, that would find a lot of uses in those hobby compilers, I think.
So another use case I see serialized CF nodes graph as an importable target. So Scala has something like TST, typed
Yeah.
serialized typed abstract syntax tree. We can have the same thing and have the graph as an importable target, like a library, like the thing. It's not
Right.
the source, but the serialized graph.
I
And
yeah. I mean, I think actually maybe we're getting
that's
close there. That
yeah,
the
that's an interesting idea.
right. So as soon as you say serialized, you lock down certain behaviors,
Yes.
and you're not allowed to change. But I
Yeah.
think a lot of what goes on right now, like I'm past the point where I'm making large, complicated changes to the ideal IR. There's a butt ton of missing optimizations. Um, at some future date, there's probably a counted loop node uh, to go help with all the standard, counted loops. There's a range check test version, which is an unsigned test, would be thrown into the ideal version. Other things that I'm looking in here, there's like just a handful. A lot of these things on a reload from a disk would simply, after you pull the graph IR in, you'd go find this piece and set it. That's just a convenience for a bunch of the outputs. This again
But
would
of
be
course, wouldn't we have to pick at which point to serialize? Maybe the ideal graph, not instruction selected graph. Although you can do that.
yeah. I mean the you could do anywhere you want. You could after parse and before opto,
Yeah, yeah, yeah,
and
yeah.
the serialized versions sort of straight up. The port to x86 would pick up new node types as part of your serialized format. You'd have to figure out, like it's likely that x86 port keeps changing for a while. Certainly, you
Mhm.
could add there's a bunch of missing ops I just haven't done.
Yeah. But the
Um,
most stable way would be the ideal graph before instruction selected, because that would be the full graph information.
right, right. And then as a serialized form, it's pretty straightforward. I certainly do like the type system in AA is fully bijection.
Mhm.
So you could write to disk and come back. I mean, but it's actually human readable. It's intended to be human readable. So if I would do a bijection to disk, I would actually make a dense version that wouldn't be human readable.
Mhm.
Um, yeah, no, I don't have any. I don't see anything going on here that would require any sort of weird special. It'd be pretty straightforward to slap it down and slap it back out.
Yeah, because that opens the door as something akin as a library. So
Basically, you get an object file version of
yeah,
things,
yes,
more or
yes.
less.
Hmm.
And I don't know. You have to give it a name,
Yeah.
and agree that we're ready to lock down. And I guess you put version numbers in to go help. Uh, I'm looking at, there's like, 15 things that would go into the code gen guy. And pretty much everywhere else, I grabbed the statics out and moved them over here one by one by one. I might be missing one or two, but not very many. So yeah, as far as I know, this would be straight up. Like things like iter peeps has a work list seed. Let's see, is that actually a global?
Mhm.
I might have yanked that global out as well. And it currently doesn't need to be, I don't see the word static anywhere in here. Yeah, maybe. Not that one either then. Nope. I think I'm pretty close now to being sort of all statics in one spot. Um, and most of them are just there for keeping people from having to call out a billion times over for the same thing.
Mhm.
So
Interesting.
yeah, I'm I've got my hands full and I have to go do, projects for money at some point too. So if you want to go write that out, feel free.
Yeah.
I'll certainly
Once
take
I
a
reach
PR.
that point, I will certainly
Yeah, sure.
mm, try to experiment with that. So when I reach that, well, why not?
Okay.
Mm.
Um, yeah, anything else? Be happy to call it if people want.
Yeah.
Quality over volume, quantity,
Anyway,
something.
anyway, it's been interesting. So
Yeah, good.
yeah.
All right. Uh, I'm gonna declaim victory here. So until we meet again,
Okay.
good night.
Bye.
Stay
Yeah.
cliff.